Hello everyone, I'm Tomer Schwartz from Fujitsu Research of Europe, now presenting my work on VPN detection with IP geolocation. Yeah, we'll go over some introduction first and over everything else. Okay, IP geolocation as a security factor has been growing over time. It's used to identify identity fraud, identity spoofing through through detection of it's through impossible travel, through inconsistent login locations, that kind of thing. But it has one major flaw, the prevalence of IP spoofing. Through VPN usage or proxy usage, any client of any sophistication can just use a VPN, hide its location very effectively, and you can't really trust the location that is presented by the IP. There's a growing market for this kind of technology through zero trust and fraud prevention. Yeah, it's 72 billion like a few years ago, and it's projected to grow to about 345 billion. So this is a big problem to solve. On the server side, proxy detection is essentially solved through the fact that proxies are on the application layer, meaning that they first have to initialize the TCP connection with a TCP handshake to the proxy, and the proxy initializes a TCP connection to the web server that is accessed afterwards. But the TLS communication has a handshake directly to the web server from the client, for privacy reasons, of course. And through discrepancy between those RTTs, where you can measure the RTT of the handshake of the TCP and separately measure the RTT of the handshake, of the TLS handshake, if there's a big discrepancy, you can tell that a proxy is being used, some sort of proxy, and that the IP you're seeing is not the client's representative IP. VPNs, on the other hand, create a tunnel on the network level, meaning that both the TCP handshake and the TLS handshake make the complete path from the client to the server, meaning that there isn't any significant difference to measure there. VPNs are difficult to detect. They are always trying to hide their presence. Usually the point, at least of commercial private VPNs, is to sort of do geolocation spoofing to access things in different locations or just to hide your identity for security reasons. So VPNs have tight security, which leads to the fact that there are many, many VPN detection methods with some flaws. It can be divided into two categories, passive detection or active detection, where passive detection is usually based on just databases of known IP to VPN mappings based on offline scans or central sniffing with behavioral analysis. Active detection has many, many methods. Fingerprinting of detecting specific ports, specific services on the server, or deep packet inspection, usually paired with machine learning or deep learning now. Some delay in RTT measurements, and the most intrusive one, in my opinion, would be running client JavaScript scripts that sort of connect to different servers and identify that there are discrepancies there. For passive detection, they're essentially very, very accurate, but mostly for known connections, meaning they'll be very, very good at detecting benign connections or connections that aren't from very sophisticated actors, which have been seen to hijack machines, use them as a proxy once, and dump them and never use them again. And of course, they are being constantly updated. They're very easy to use. Most commercial VPN detection systems are this kind of systems. But the big limitation, of course, is that they can't detect these sophisticated actors, and they sort of create an arms race of just IP rotation by the VPN services. VPN services keep rotating out IPs, trying to keep ahead of the detection services, and it's just a tug of war of who gets the most IPs through. Okay, so active detection, on the other hand, usually isn't based on specific IPs, it's more on behaviors. But the main problem with that is most of these are pretty easy to mitigate. Like fingerprinting through detection of specific ports or specific services. It's pretty easy to change, even on the configuration size. Even the deep packet inspection solutions have been mitigated quite easily by updates to the VPN code, to the protocols, and stuff like that. Again, which leads to another kinds of armories between either the VPN services or malicious actors that are trying to improve the VPN service all the time against defense solutions. So when looking at that, we thought that there's something more to discover here, that the most detection methods aren't good enough, at least for malicious detection. Having a known IP to VPN database is good if you want to detect just regular use, but for the truly malicious, sophisticated actors, it will almost never catch them. And most active solutions on the are just not good enough, at least in my opinion. They have pretty easy to mitigate. You can see the papers always evolving, like, okay, we tried this. A year later, there's a new paper. We were mitigated, so we were trying that. And we wanted to try to find something closer to proxy detection in the sense that it's a very inherent fact of proxy detection that is very hard to change without completely changing the protocol. Okay, so let's look at the communication delay. We have, of course, the main client-to-server RTT, which can be divided into two sections, client to VPN and VPN to server. And in the same way that we can measure the RTT for the proxy detection, we can measure the full RTT from the client to the server using handshake communication. And what we would like to find is the discrepancy between the VSRTT and the CSRTT, if a VPN is really in that, is a stepping stone in that communication. So we were thinking, what information do we have? The naive approach would be to try to ping the server, access it directly, maybe traceroute. Those work for some VPNs, but the sophisticated actors and main services just tend to block that kind of communication. So we're thinking, okay, we can use IP geolocation here. The IP the server sees is when a VPN is used, it is the VPN server's IP, and when a client is used, it's a representative IP of the client. And using IP geolocation, we can get a location from that area. And we use a pretty intuitive assumption, but one we, of course, are going to prove, that the main cause of communication delay is the physical distance between the devices communicating, at least in modern networks. That's a pretty big caveat, but it's important. And based on that, I thought a pretty cool idea, I think. Instead of communicating with a VPN, we can communicate with a representative landmark in that area. Using IP geolocation, and specifically we used RIPE Atlas, which is a ground truth landmark, probe or landmark service. We can find a landmark in that area and communicate with it instead. Just ping it, because they're all active, open to interactions, and based on that measurement, in simplified terms, if there's a significant difference between the expected RTT that is measured from the landmark to the server and the RTT that is measured from the client to the server, we know that there's a stepping stone there. Essentially, the detection process is quite simple, quite straightforward. There's initial client-to-server RTT measurement. We can measure both the TLS and TCP. Based on that, we can initially start with simple proxy detection, because there's no need to access a landmark if we don't have to. If a proxy is detected, we just return that. And following that, we locate nearby landmarks. If they exist, measure the RTT to them, and essentially use this pretty simple formula to detect them. The error margin is calculated using the RTT. It is a deeper dive for a deeper dive on how it's calculated, you can look at the paper, and it's basically based on the expected ratio of what the RTT difference is based on expected jitter for that length of communication and maybe congestion. And of course, if the connection is unstable, we sort of add that to add some buffer and of course the expected error of the geolocation. Okay, experiment is quite straightforward. We set up 8 servers in diversified Azure data center locations. Each server runs a Flask detection server paired with a sniffing tool or a sniffing script that measures the RTT and communicates that to the server. And we use RIPE Atlas probes as ground truth landmarks. They're very easy to use, open to ping, and quite reliable. And we use the IP info geolocation service. Yeah, for the client, that was a bit harder to set up. Specifically, also set 8 clients. Each client uses a Python script with a Selenium Chrome driver to make the connection as authentic as possible to like real-world use. We use the PIA and Pure VPN VPN services. We specifically didn't use the top VPN services because like ExpressVPN and NordVPN act as proxies in their communication style, which was a bit surprising. So we had to find ones that make a full tunnel, especially because a big issue we ran into initially is how do we get the same amount of VPN locations that you get from VPN services? You have access to thousands or tens of thousands of unique IPs, unique locations, and no service for direct clients works that way. At least I couldn't find any. So I used the fact that proxy communication breaks and measured just the TCP connection for residential IP proxy services, specific service bright data. Then I got access to a lot of IPs. For the experiment, I didn't detect proxies because that's a solved issue. I focused just on the VPN detection. Yeah, we had over 130K measurements with over 24,000 unique IPs, hopefully corresponding to unique locations. And yeah, as an initial validation of our assumption, we can see here that a very good correlation between distance and RTT. Of course, I use the full distance traveled from the client to the VPN and from the VPN to the server. And yeah, there's also a pretty intuitive validation of our thought process. On the left-hand side, you can see the direct client ratio between the full client to server RTT and the landmark to server RTT. You can see that it's pretty definitely around 0. Of course, with some variation, network communication is inherently unstable. And for VPN communication, you see widely varying options. Of course, we had some that are below 0, which were through severe congestion and stuff like that, which is bound to happen at times. We also use the confidence value for detection by how wide the margin of detection is. And yeah, for the pure binary detection for worldwide communication, we had about 85% accuracy. But when you increase the confidence even to 0.5, you're up to about 90% and over that for full confidence. Specifically, we wanted to highlight the regional effect that we saw. We knew that it had to be modern networks for it to be truly reliable. And you can see the effect of slightly less modern networks like in Africa, South America, and parts of Asia that have a quite significantly lower precision or accuracy. But let's say North America, Europe, Oceania, you can see that it's about 90% or over. Yeah, so an important thing we thought about initially was maliciousness. The passive detection solutions are very good at detecting overall, just standard VPN usage with regular services, but would essentially be supposed to be quite bad at detecting first-time VPN usage or hijacked machines, that kind of stuff. But our solution can detect that on first iteration. So to have a greater indication of maliciousness, we thought that a hybrid approach of using both a passive detection and our solution in tandem would be a very good indicator. For example, if the passive detection doesn't detect and we have a detection, that could be an indicator of a new VPN or a VPN that is used maliciously and not by one of the standard known VPN services. There are also, of course, some limitations. As the distance between the devices shortens, the effect of standard network jitter becomes more significant. And we were wondering what the exact distance where that effect would be. What's the distance where jitter is essentially more important than distance? And you can see in the graph on the right that essentially up to 500 kilometer distance between the client and the VPN, our detection rate is 0. We can't really detect on that kind of distance, but on an international scale, that is not very significant. And if what you're trying to detect is geolocation spoofing, that is not very significant either. And above 500 kilometers, you see a very steep increase of confidence in the detection, and it, of course, increases as the distance increases. And a pretty severe limitation is the landmark coverage, as it is now, for residential IPs mostly. Over 50% of the residential IPs that we accessed didn't have a probe in the range that we specified. We specified specifically 200 kilometers. This is based on what the expected geolocation error is in different areas. But it's probably worth exploring to increase that range or finding ways to increase the coverage of probes all around the world. Yeah, as I stated, if someone just wants to hide their specific IP at encryption using a closely located VPN completely nullifies our solution. And something more drastic that could be done is sort of creating a new protocol that breaks the tunnel, in essence, that both the TCP and the TLS need to do a handshake with the VPN server and then another handshake with the destination server. With that kind of solution, our method would not work, but that leads to pretty severe privacy issues. The VPN server would essentially have access to the data being passed through in an unencrypted manner, or it would require another layer of encryption, which creates a pretty significant technical overhead, and it would take a while, I think, to implement. Of course, if the VPN server spoofs its location in some way by poisoning IP geolocation databases or anything like that, that would be a major issue. But I think it would be a bit difficult to mitigate, in essence. Okay, so this is SNITCH. Server-side VPN detection solution. It uses real-time network delay, measurements, and geolocated landmarks, essentially bypassing the need to communicate directly with the VPN server, which is usually isn't very cooperative. And that way it overcomes the limitations of previous solution, doesn't require prior knowledge of the passive detection methods, it doesn't require interaction with the VPN server for the active detection methods. We have about 90% detection accuracy worldwide with a confidence of 0.5 and up to 93% accuracy for modern networks. We're using essentially a characteristic of the distance traveled, which is more than what would be expected by the representative IP, which I believe would be quite hard to mitigate. Yeah, thanks for listening.
Hi, thank you. It was a great presentation. So I think with respect to server-side detection, I think there has been some work that has already been done, and I think you also highlight that. I just wanted to know specifically that are you aware of a work that was presented at USNICS last year called as calculatency, which also tries to basically, measure the, try to detect, VPN servers. And could you comment on, how your work differs or, compares with that work in trying to detect VPN servers with just latency measurements?
Yeah, I think I referenced that directly in the paper. Like there are a lot of different sort of state-of-the-art solutions for VPN detection. So I wrote a lot in the paper about that, but I felt like I didn't have the time in this presentation. So yeah, I address a lot of that in the paper.
Could you just maybe mention like how it differs from that, like this approach? Is it just the fact that you are selecting additional landmarks, or is there something else?
If I remember their solution correctly, they did require some communication with the VPN server. They used, I might not remember the exact paper, but one of the newer solutions that I saw last year used both just pinging, the direct ping to the VPN server, or zero trace, which is like a TCP-based trace route, which requires that the VPN server, or at least close by routers, return an RTT exceeded message, which is not given. So I sort of circumvent that by not trying to communicate with the VPN server at all.
Got it. Yeah, thank you.
Hi, Lars Eggert, Mozilla. Thanks for the nice talk. I didn't read your paper, so it might be in there. But I wondered if you looked at routing asymmetries and how that affects your detection ability.
I didn't look at that directly, but I think over significant distances, just worldwide, like international communication, that becomes less significant. But as the distance shortens, just bad network conditions or even routing errors can be an effect, yeah.
So I think you're seeing some of it in the data because you showed that in some regions it works better than others. And I think the regions where it doesn't work are those where you have more asymmetry in the routing system. The other reaction I had was to your mitigation slide, because it seems like you're using discrepancy between layer 4 information and layer 7 information that's visible at the server. And that's pretty clever. But that just means that the VPN servers need to do an HTTP proxy and basically issue the requests themselves, and then that discrepancy goes away. That's, I think, the mitigation that you hinted at, and that sort of exists already, right? HTTP proxies are there. Obviously, they only work for the web, but the web is a lot.
Yeah, if it just acts as a standard proxy, then it would be actually easier to detect, but it needs to sort of implement you mean a standard HTTP proxy, not have the additional SSL layer?
If the VPN server acts as a proxy and issues the requests towards the destination server, you don't have an RTT difference between what you observe at layer 4 and at layer 7.
Sure, but if an SSL connection is established, it's usually established directly with the client?
Usually yes, but what if it wasn't?
Yeah, if it wasn't, then my solution will probably not work. That is true.
Thank you.
Thank you, everyone.
Next, we have Damiano to discuss public IP block list, explain internet video.
Thank you. Good morning, everyone. I'm Damiano Ravalico. I'm a second-year PhD student at the University of Trieste. And today I will introduce our paper about using public blocklists to explain the internet radiation. Nowadays, many scanners contact hosts to find those that are vulnerable. And this is not a problem in cybersecurity, and network telescopes are very useful to study and identify the behavior of these scanners. A network telescope, often called also darknet, is a set of IP addresses that do not host any service or any client. So they capture only unsolicited traffic arriving from scanners, botnets, and similar. This type of traffic is also known as internet radiation. Given the nature of captured traffic, these telescopes are very useful tools to identify and study malicious behavior and activity on the network. However, they come with a cost, since their deployment and management are very costly. Blocklists are a list of entities, for example, IP addresses or URLs, that are supposed to perform some type of malicious activity on the network. For example, a blocklist may report IPs belonging to a botnet. A blocklist can be used to block the traffic from or to its sources, its entries. For example, it can be used in firewalls or email filters. This list can be either public or proprietary, but there exist many cyber threat intelligence sources that release and distribute publicly this blocklist that aggregate data from multiple cybersecurity sources. This blocklist can represent a possible cheaper alternative to the deployment of the telescopes. However, it is not easy to evaluate if they work well in listing malicious actors of the network. In our work, we ask whether this list alone can explain the internet radiation, or if the deployment of new telescopes are still useful. To answer this main question, we set 4 different result questions. In the first one, we analyze the coverage provided by this blocklist in terms of traffic received by telescopes, by network telescopes. This leads to questioning if telescopes observe new IPs earlier with respect to blocklist, or even if they are synchronized. Then we investigate about blocklist quality, and we conclude our paper by analyzing the IPs that are observed in the telescopes, so they are active, but are never listed by any blocklist. Our collection period ranges from July 5th to September 10th of the 2024. However, in the following analysis, you will see that some days will be missing. This is due to a problem in our cluster. The dataset of the telescope is composed by 4 different telescopes that differs in size as well as geographical position. In the table, you can see the information about these 4 telescopes. Since network telescopes receive a lot of traffic, including backscattering, that is traffic generated by devices that are misconfigured or compromised, we want to focus only on real malicious scanners. So we discard all the packets that are not pure TCP, so that have a flag different from the seen one. Additionally, following previous work, we get rid of occasional sources that contact the telescopes only sometimes by applying a second filter that removes all the sources that send less than 5 packets per each /24 subnet. For example, looking at T3, that is a /22 subnet, we remove all sources that send less than 20 packets. In this way, we remove only the 13% of the total traffic. For the blocklist dataset, we download 50 public blocklists every day using 2 different sources. The first one is FilterList, that is an online aggregator that lists a lot of blocklists, but we focus only on those related to IPv4 and that are related to malicious activity. The remaining half of the blocklist are taken from a previous work that have similar criteria to select blocklist. In this way, we collect 16.5 million of unique IP addresses for a total of 14 gigabytes. Additionally, telescopes are known to receive traffic also from well-known beginning scanners that do not have any malicious intent, for example, Shodan, but they scan and monitor the internet for analysis and research. To consider also the activity of this benevolent scanner, we employ a dataset released in the literature that includes 41 different organizations. For some of them, we will see that we are able to update the list. It is interesting to observe that 27% of the IPs present in this dataset is also listed by a blocklist, indicating that they list some benign scanners, even if they should focus only on malicious activity. We now move to the result part, starting from research question number 1, in which we evaluated the coverage provided by the blocklist. We define the coverage as the percentage of IPs or the packets that they send that are observed in the telescopes, but that is also listed in at least one blocklist. Note that we consider the union of all the blocklists with also the addition of the benevolent scanners, that is a fixed set during the entire period, and we compute the coverage day by day. In this plot, you can see the date on the x-axis, while the coverage in terms of percentage of IP on the y-axis, and each telescope is represented by a curve. We can see that there is a consistent pattern also for peaks and drops. This is interesting because these drops could indicate the beginning of a new campaign of scanning from some malicious actors, but Blocklist needs some days to report them, since after the peaks, the trend returns to the previous value with some days of delay. For example, this is a major example, and after some days, the coverage returns to 80%. Even if we reach a high median coverage in the order of 80 to 85%, we report that only 71% of the total IPs observed in the telescopes are reported by at least one blocklist during the entire period. So there is a high dynamism about sources that contact the telescopes and then disappear. But blocklists miss these IPs. We repeat the same analysis, but in the case of coverage of the traffic. So in the traffic generated by IPs observed in the telescopes that are also reported in the blocklist. In this case, the picture is noisier, and only in the first period, T1 and T3 have a similar pattern, with T2 showing a lower percentage, while T0, that is very far away from the other telescopes, show a very different behavior. Please note that T2 previously hosted some production services, so it may explain the different coverage provided and the lower coverage. In general, there are many more peaks and drops, and the median coverage is different across different telescopes. But the key point is that we prove that the coverage provided by Blocklist with the addition of also acknowledged scanners is high, but they miss the most dynamic sources contacting the telescopes. Then we investigate on research question 2, in which we ask if telescopes observe some sources in advance with respect to the blocklist, so as we speculated in the previous analysis. To do this, we calculate the delays as following. We consider the IPs contacting the telescopes on a given day, that we call a reference day, and then we compute the overlap between this set of IPs and the cumulative set given by the union of all the blocklists and also the begin scanners for the 30 consecutive days. We repeat this procedure for 30 different reference days, and then we compute the average statistics. The result of this process is shown in this plot. On the x-axis, there is the number of days following the reference day, while on the y-axis, there is the coverage in terms of percentage of IPs. Here we can see that there is a consistent trend across different telescopes. In 5 days, the coverage grows up to 90%, but the curves never reach the maximum. After reaching a coverage of about 90 to 92%, the curve saturates. This suggests that the blocklists do not capture a significant portion of potentially malicious sources that are contacting the telescopes, even with some days of delay. As for research question number 1, we repeat the same analysis, but in the case of the traffic. In the plot, you can see on the y-axis the coverage in terms of packets that sources listed by the blocklist observed in the telescopes perform. In this case, there are some differences, starting from the increase that is up to 20% in 5 days. But then there is, and it is shared across different telescopes, even if in different terms. But in this case, there is an earlier saturation. However, the key finding is that we've shown that telescopes receive some IPs in advance, and also they receive a lot of more sources with respect to blocklist. We continue by examining the activity of the most active IPs contacting the telescopes in terms of numbers of packets that they send, to verify if the blocklist captured them. We define these IPs as top talkers. Since the definition of a top talker is arbitrary, we choose to select the 150 daily most active IPs contacting each telescopes, and then merge them all together by repeating this for each day of our dataset. The figure illustrates the result of this process. On the x-axis you have the date, while on the y-axis there is the number of top talkers sorted by the first appearance in the telescope. A red point indicates that a given top talker is active in the telescopes and also reported in at least one blocklist, blue if it is active but not reported, and white if it is not active in the telescope. We observe different behaviors, starting from the fact that there is 130 IPs that contact the telescopes every day, so they are always active, but only a small portion of them are reported by the blocklist. In total, 40% of the total IPs are never reported by any blocklist, and also in this case there are a small portion that are always active. So we can affirm that blocklist miss some of the most aggressive IPs contacting the telescopes. Additionally, on the first day, more than half of the total IPs are never listed, are not listed, and eventually, with a median delay of 4 days, they are added by some blocklist. Finally, we can observe that many IPs have a pattern of insert and remove from the blocklist even multiple times. In conclusion, we can say that relying only on the blocklist would lead to missing some of the most active IPs contacting the telescopes. We proceed to evaluate the effectiveness of the blocklist in terms of completeness and specificity, to define how much a blocklist covers IP addresses observed in the telescopes and how much it is precise in report them. To do this, we borrowed the idea from precision and recall metrics. In particular, we define the recall as the portion of IPs seen in the telescopes that are included in a given blocklist, and the precision as the portion of IPs reported in the blocklist that are also observed to be active in the telescopes. A maximum recall would mean that all IPs of the telescopes are inside the blocklist, and a maximum precision would indicate that all IPs from the blocklist are seen active in the telescopes. Here you can see these two metrics. On the x-axis there is the recall as percentage, while on the y-axis there is the precision as percentage. Each point indicates the 50 different blocklists, and the color indicates the size of the blocklist. The brighter, the bigger. The first thing that we can observe is that there are a lot of Blocklists that have bot metrics under 20%, so they contribute very small to the coverage of the internet radiation. Some blocklists show very high precision, indicating that they are very good in list some type of malicious activity. For example, the Mirai Tracker blocklist, having a precision higher than 80%, are very good in tracking IPs belonging to the Mirai botnet. In general, higher recall comes with lower precision, and it can be seen that big blocklists have high recall, while small blocklists have high precision, with only Turis is in the middle with bot metrics nearly 40%. In conclusion, we can affirm that only a few blocklists cover most telescope traffic, while others are very useful in identifying some particular type of events. We conclude our work by characterizing the IPs that are never inserted any blocklist, but that are observed contacting the telescopes. During the time period, about 29% of the total IPs are never reported by any blocklist, even if it is interesting to observe that they generate only the 10% of the total traffic. To investigate about these IPs, we use two different methods. The first one is the reverse DNS, in which we aim to obtain the fully qualifying domain name to then apply some type of regular expression and classify these IPs. We define three categories: additional and begin scanners, that, as I mentioned in the introduction, are some IPs that are begin and that are not listed in the original dataset. Broadband subscription is the second category, and then cloud provider. Next, for the IPs for which we cannot obtain any information using the first method, we employ the MaxMind database to try to obtain the autonomous system and the country related to those IPs. In this slide, you can see the result of this process. In the table, on the top rows, there is the categorization derived from reverse DNS, with the number of IPs for each category. Please note that the scanner category, scanner performing some type of begin activity in the telescopes, are only 188, but they generate a lot of the total traffic, nearly 9%. In the middle, there are the top three autonomous systems, and in this case, China dominates. Only for a small portion of the total IPs, we were not able to obtain any information. And we suppose that the category of broadband subscription and cloud provider IPs may belong to compromised devices. In this work, we showed that a significant portion of IPs seen in the telescopes are never inserted by any blocklist, so the blocklists are missing some potentially malicious scanners. Additionally, telescopes are very useful because they can observe some sources in advance with respect to blocklist, and blocklist needs even some days to report some malicious actors. Different blocklists provide different precision recall, different quality, and we can conclude by saying that telescopes are still an important tool, and new deployments are very useful, since telescopes, as I previously said, observe many IPs in advance, but also have a view that is more updated with respect to the blocklist. In future, we plan to collaborate to try to reach a blocklist operator to collaborate and use honeypots to repeat this analysis. Thank you for the attention.
Hi, interesting talk. Wes Hardiker, USC ISI. I've done a lot of sort of research in this area as well. Telescopes are definitely useful, not for just detecting scanners, but for actually trying to figure out what scanners are doing. I guess the one problem that I had with some of your conclusions are actually right on the screen with respect to potentially malicious scanners.
Yes.
And the reality is that Blocklists maybe shouldn't be blocking all of those addresses, right? So it's interesting that 29% of the addresses you've found are not on Blocklists, But at the same time, some of them could be students at a research university that are only trying to figure out what's out there, or other benign, scanners and things like that. So the problem is that when you look at 50 block lists, if they're doing a good job of finding only malicious things and blocking malicious things, they probably shouldn't be blocking everything. Is that a fair conclusion?
In general, I think that as we see in this analysis, a lot of these block lists are not doing a good job, since they show good precision but a very small recall. And also, maybe there is more, we should have a larger data set to verify the behavior of this block list in the long term. Here we have only nearly 2 months, so maybe we should enlarge the dates range.
So concluding really quickly, because I know we're going to run out of time, could you go back to the graph you just showed?
Here?
Yeah, because that's a perfect example, right? The Mirai tracker, you would expect to only be blocking things from Mirai botnets. So of course it's going to miss a lot of things. Its purpose is very specific.
Yes.
So it's not trying to capture everything.
Yes, of course.
Okay.
Cool. Very interesting talk.
Thank you.
I just one question. So you mentioned something about that there is a delay with respect to when IPs are, introduced in a block list in comparison to when you see in your telescope. So do you have any insights of, what sorts of reasons are there for those delay? Like any comments or any thoughts from your experiments that you could find out?
It is difficult to define why there is this delay, because in general block list operators are not very transparent about how they collect IPs, how they insert IPs, the update period. So we do not further investigate about this. We only want to show that in general telescopes are, how can I say it, more useful, are still useful to cybersecurity picture.
Yeah, thanks.
Thank you.
Hi, great talk.
Thank you.
I have a question about when you use different telescopes in
Yes.
different regions, did you see any significant discrepancies between
Sorry,
what...
I didn't hear you.
Yeah, sorry. You use multiple telescopes, right?
Multiple?
Yeah.
Multiple telescopes?
Yes.
Yes,
Yeah.
of course.
So did you see any significant differences between scanners that access them in different regions? Like, did you analyze that?
In this case, we do not investigate about this, because my supervisors and his team already investigated this particular topic in previous work that we cite in our paper. So this is not the focus of our work.
Sure, I'll read it. Thanks.
Thank you.
Okay, I think I have a last question. Can you go to the conclusion page?
Yes.
Last you mentioned that potentially honeypot can be deployed, right, to observe more behaviors. Even before the honeypot is deployed, can we get some timing information or the scanning pattern from the telescope?
Sorry, can you repeat? I didn't hear you.
Can we get
I'm really sorry.
timing and sequence information from the telescope operators?
From the telescope's operator?
Right.
From the block list operator, you mean?
Not blacklist is just a list of IPs, right? For the telescope, do you give information then, including the probing behavior and other factors?
I'm really sorry. I can't understand the question.
Okay,
sorry.
Sure. Yeah, maybe we can follow up.
We can talk later.
Offline, sure. Okay, let's the second speaker.
Thank you.
Okay, great. Next, we have Christoph from Mozilla to discuss the status of HTTPS adoption on the internet. Thank you.
Good morning. Today, I want to invite you to look at a success story with me. The success story of HTTPS adoption on the web. Over 30 years ago, in August 91, Tim Berners-Lee published a blog post sharing information about his World Wide Web project. With the words, "Try it," he encouraged the population to make use of it. And since then, billions have, and I think for most of us, the web has become an integral part of our daily lives. Since its inception, the web has relied on HTTP. The downside of HTTP is that it transfers data in the clear, allowing an attacker to view, steal, or even modify the transferred data. Carrying HTTP over TLS allows to overcome this security shortcoming by creating a secure and encrypted connection between the client and the server. Today I bring you two different parts about the success story of HTTPS adoption on the web. First, I want to survey real quick the different upgrading mechanisms. And then second, I want to show you real-world Firefox release user data showing what the state of HTTPS adoption is on the web. Let's start by looking at the different upgrading mechanisms, but before that, there is one important thing. For this measurement study, we looked specifically at top-level loads. And the top-level load, or document load, is the load of the main HTML document. That is basically, or simplified, the URL that is displayed in the URL bar. In contrast, we have all the different sub-resources like images, styles, and scripts. A different thing to remember is that there are client upgrading mechanisms and server-side upgrading mechanisms. We begin by surveying all the server-side upgrading mechanisms and the different possibilities for web developers to upgrade more content to HTTPS. The third thing I want to highlight is upgrading secure requests, which is a CSP directive. Now, most of you probably know CSP for being an effective countermeasure against cross-site scripting. But CSP also holds a directive that is called upgrading secure requests. For simplification reasons, I'm using here the meta tag for the content security policy, but obviously it works the same if you want to use an HTTP response header. What upgrading secure requests does, it brute forces all sub-resources within a web page to be upgraded to HTTPS. And more importantly for this topic, and most people don't know that, upgrading secure requests also applies to same origin top-level navigations. It literally forces all requests to be upgraded to HTTPS. There is no fallback mechanism. So if the server doesn't respond to an HTTPS request, it simply fails. The next thing I want to look into is HSTS, or HTTP String Transport Security. On a high level, it allows a server to signal to the browser, please, I speak HTTPS, please only connect over HTTPS. In more detail, the browser tries to connect, sending a GET request to the server. If the server wants to signal the browser to use HSTS, it has to do that redirect dance. And the redirect dance means the strict transport HTTP response header is discarded by the browser if it's not sent over HTTPS. So first the server has to redirect to HTTPS before actually signaling the browser or transmit that signal. The browser then obviously caches that signal, and from that point on forward, it always connects through HTTPS to that web server. One of the downsides or of the drawbacks of HSDS is that the initial request is still over HTTP, which allows an attacker to provide some form of downgrade attack. To overcome that problem, browsers started to incorporate HSDS preload lists, which is really a list of all servers or of all domains that support HTTPS and want to be connected only over HTTPS. There is a service where you can actually enter your domain name to get on that list. I looked it up, and currently Firefox hosts a little bit over 100,000 entries in the HSDS preload list. Like, obviously, as you can imagine, that doesn't scale to the size of the internet. However, and I think this is important, most of the traffic that happens on the web happens on top sites, right? Like Google, Facebook, Amazon, and whatnot. So maintaining that list obviously makes sense. But again, it does not scale to the size of the internet, and we want a solution that works for everything. A relatively new, or at least in Firefox, it's a new feature, is HTTPS resource records. And basically, we, on a high level, we store information in the DNS record that delivers configuration information for how to access a serving using HTTPS. So by querying information from the DNS server, we already have the information, oh, that server or that domain supports HTTPS, and the browser can use that information to connect using HTTPS. So now those are all the server-side mechanisms that a web developer can use to upgrade their connections to HTTPS. But obviously, we also want to look at the client side of things, what the browser can do. First, there are web extensions. For all of you who don't know what web extensions are, you can basically install a web extension to your browser, and the browser exposes a set of privileged JavaScript APIs to a web extensions that a web extension can take advantage of. Using that, the web extension can intercept outgoing requests and modify, and through that upgrade those requests. One of the downsides with that approach is that end users have to actively install certain web extensions. And with that, the approach by itself is already limited, that only security-aware users will install an extensions like, for example, HTTPS Everywhere. HTTPS Everywhere is the most well-known web extension for upgrading web content to HTTPS. Obviously, there are many more. But even EFF, who maintains HTTPS Everywhere, recently decided to discontinue working on it because they said all the in-browser upgrading mechanisms provide better service than they can offer through the extension. And with that, now we transition into all the different upgrading mechanisms in the browser. It's important to know that all the different browsers by now support some form of upgrading mechanism. But obviously, I can talk the most about Firefox because I've been heavily involved in the implementation of HTTPS and HTTPS first and HTTPS only. Let's look at the historic browser connection model. If you enter http://example.com, or also if you omit the scheme and just type example.com in the URL bar, a browser used to connect using HTTP. Similar, if you click a link on the, or used to click a link on the web, and it was HTTP, the browser happily was connecting over HTTP. But that changed with the introductions of all the in-browser upgrading mechanisms. The idea is that we have sufficient website support HTTPS that we can shift the model and first try to connect using HTTPS and fall back to HTTP if necessary. Again, refresh your mental model about the HSDS connection model, right? So the initial connection was over HTTP. We do that funny redirect dance so we can finally connect over HTTPS going forward. With HTTPS first and HTTPS only mode in Firefox, we flip that around. We try to connect using HTTPS, And then we kick off a timer. And it's always so great to tell that story, because what you see here, the 2,200 milliseconds, sounds very easy, but this was empirically evaluated, and we keep modifying and changing and fine-tuning that tuner to provide the best user experience to our end users. For now, keep in mind that we kick off the timer. If the website reports an error or an OK, then we can continue, well, simplified. If the server allows to connect over HTTPS, it's all good. If the server reports an error, then Firefox can deal with the error and we initiate a downgrade mechanisms. But if after those 2,000 milliseconds nothing has happened, we kick off a background request. And that background request, we strip path information, query parameters, cookies, and we only send that to the main domain, figuring out if that host even exists, because the end user might have a typo in their URL. So now it gets interesting, because if that background request returns a result faster than the actual upgraded request, then it's a very strong indicator that the result will return in a timeout. If you don't have any mechanism like that, then a browser would have to wait till the request times out, which is sometimes even 90 seconds, which is unacceptable in terms of a user experience. But if that background request returns a result faster, then it's a very strong indicator that the result will return in a timeout, and we can deal with it. So here, in the case of HTTPS only mode, we provide an interstitial page, or in the more fine-grained, user-experienced version HTTPS first, we do an automatic downgrade to HTTP. Because what we have learned from our users is, hey, Firefox, if you can make it secure, please do. And if not, don't bother me. I want my content. With that, we conclude the first part, and now we get into the more exciting things, the actual measurements. So 10 years ago, 30% of HTTPS adoption, which is rather low, and I want to go back to refer to what Nick said in the morning when he was on honeymoon in 2011. He probably not only worried about all the JavaScript problems, but also probably had to worry about an active network attacker injecting additional JavaScript on the fly. But anyway, in 2014, we were facing roughly 30% of HTTPS adoption. And if you look at 2024, we are at over 80%. And this is quite a success story by itself. If we look at that, there are multiple things that contributed to that success. Obviously, what we have seen now was upgrading secure requests, HSTS, then obviously Let's Encrypt played a big role in it, but also probably the secure context specification that only allows to expose powerful APIs if in an HTTPS context or in a secure context. Firefox and other browsers started to stop mixed content downloads, which means you are on a top-level HTTPS page, and when you want to download something from, let's say, your bank, if that is over HTTP, then Firefox started to display a warning. We stopped FTP support. For those of you who remember, FTP was a big portion in the browser, but FTP is also transferred in the clear. And one of the other downsides is that HSTS doesn't even apply to FTP. So after a long time, we were able to deprecate FTP in the browser completely. There was also search engine boosting your rank if you supported HTTPS. So in summary, there were not one single thing that allowed us to magically have more HTTPS adoption. It was a continuous effort from browser vendors, from the web community, from all of the academic community as well. I want to show you some measurement details now of the state of HTTPS adoption on the web. And for that, we collected data from over 140 million Firefox release users from all over the world. And that data was collected for the Firefox 134 release cycle between January 7th and February 3rd this year. So this is really fresh off the press data. We first looked at adoption in different geographical regions. And if you look here, for example, in the US, in Europe, and in Oceania, we have more than 95% of HTTPS adoption. But if you look at the global south, like Asia, South America, and Africa, it's more around 80%. For our study, we also looked at the UN 10 least developed countries in the world because we wanted to figure out if there is a correlation between higher developed countries and lower developed countries. If we look a little bit more closely here, the global north, we have more than 95% of HTTPS adoption, and in the global south, it's only around 82% of HTTPS adoption. So there is quite a gap. And if we look yet a little more closely, like for example, Denmark or Norway, with the highest measured rate of HTTPS adoption, with together those four countries, 97.5%. And if we look at the lower end of our measurements, which is Uganda, Myanmar, or Sudan, Sudan only having 51% of HTTPS adoption, right? There is still quite a difference. 40% is quite a big difference in terms of HTTPS adoption. We then evaluated if there is differences between the different operating systems, right? We looked at Windows, Mac OS, Linux, and Android. And on a high level, that all looks very identical. We roughly have 2 to 5% of HTTP content. But if you look at Linux, for example, we saw that there is 10.5% of local HTTP traffic. And that is, we reason that it's mostly system administrators using or relying on Linux for setting up printers and routers, and hence doing a lot of the work in local IP ranges which are not upgradable. Non-publicly resolvable domain names such as router.local or 192.168.1.1 are not upgradable to HTTPS. But in summary, we didn't really see any big differences in terms of HTTPS adoption on the different operating systems. So now, if there is only one thing I want to give you on the way from this talk, then it's the following 2 slides and probably the next 30 seconds. So what we measured is in 90.4%, all connections already start out using HTTPS, which is very, very big in my opinion. 2.4% is still relying on HTTP, a very small fraction, and 5.5% are in the local IP ranges. And then that black bar here in the middle, that is all the content or all the connections that we can upgrade using all the different upgrading mechanisms that we have developed. And before we look at that in more detail, there is one thing that is very important to mention. In Firefox, when we do those measurements, we measure them in an order, which means HSDS, if that already does the upgrade, then we don't measure it again if HTTPS first or HTTPS only would have upgraded it. So the order in which we record it is HSDS, upgrade in secure request, HTTPS RR, basically everything that is coming from the server, which allows web developers to get a better understanding if their upgrading mechanisms work. And then we have HTTPS only, HTTPS first, the upgrading mechanisms in the browser, and then at the very end, it is web extensions. With that in mind, we now look at, or we see that HSDS is responsible for the majority of upgrades in the browser. Then we have HTTPS first with over 30%, and only a smaller role in that big pie play web extensions, HTTPS only, HTTPS RR, and CSP upgrading secure requests. It seems I'm running out of time, but we are coming to the end of the talk anyway. I think in conclusion, what we all can agree on, it's a success story. and coming from only 30% of HTTPS adoption to 92% if we include the upgradable content, we can conclude that HTTPS has become the default on the web, which is really great to see. But we are not quite there yet, right? In the paper, we discuss different options to upgrade maybe the long tail of the web, if that is possible, or we were speculating about integrating some form of allow list for HTTP content, basically flipping the model around of having an HSTS list to a legacy HTTP list. Or we can also consider that at a specific point in time, we say, well, every domain that gets registered from this point forward, web browsers will only connect using HTTPS. And if that domain was registered before that specific date, we could allow the legacy content to be displayed using HTTP. But again, in summary, we have come a long way. I'm very, very proud that we got this far and having HTTPS become the default on the web. Thank you so much.
Yeah, thanks, Christoph, for the rare, successful, bright story in the darkness of cybersecurity. Any questions?
Thank you for the nice work and nice presentation. So I had more of a clarification question with respect to the adoption. So could you shed some light on what kind of data you collect from let's say the client end? I could see that you had statistics related to operating system, geographical location, or maybe to some extent the kind of websites that the user are visiting. So I'm 100% sure there are measures that you have taken to do that collection in a privacy-preserving manner. But could you just maybe put your thoughts out on what kind of data is collected?
Yeah. So we have very, very strong data privacy principles in place. And that is also one of the reasons that, for example, we cannot create that legacy HTTP content ourselves, because obviously that would be nice, but that would, for example, violate our data privacy principles because we don't collect the actual domain that an end user is visiting. What we are collecting, however, is single bits of information, meaning, okay, the content was over HTTPS or not, right? Or the content was upgraded by HSTS or not. Like that kind of data we collect. And we also collect data in terms of region, depending on, I think it's the domain list, the public suffix list, right? So whether you are in Sudan or in the US.
Got it. Yeah, so I just had a follow-up onto that. By any chance, do you collect URLs? Because I come from the censorship background, and the idea is, it's very hard for us to even collect domains which are blocked. And I think browsers is a very good way to actually check, if there is some website or some domain that wasn't accessible for, any sort of reason. And if that data could be public, it could really help, censorship circumvention or detection and all those kinds of techniques. But I think you do not collect it, so I think that's totally fine. Thank you.
Of course.
Thank you for the great presentation and the important work in this area. I was wondering, do you also collect data on how the HTTPS adoption evolves over time on internal networks? Is that improving as well? Or can we do also more to improve that?
Yeah, well, again, data collection is a very, very important thing. And we recently, I think we delete all the data that has been older than 2 years. So that kind of data collection is obviously problematic. Even like if we go back here to what we collect here, like that data, right? We are able to have the data because we are share it with Let's Encrypt, right? So that's why we can present that kind of historic data. But since this is a completely safe space, and we are very explicit in the paper about that as well, we measured HTTPS adoption a little bit different in that graph than what we are doing now. So we have way more precision in terms of what counts as a top-level load, for example, versus an iframe load, right? And that is a very important distinction on the web as well. But answering your question, it's not easily answerable.
Okay, thank you.
While we are taking the next question, the last speaker, can you go to the stage to set the laptop up? Yeah, please.
Very cool talk. If you can go to the last slide with that graph, I was just curious if you had a breakdown about HSTS versus the HSTS preload list and kind of the relative importance of those two.
Now you tell me. Obviously, that would be very nice to know, but we don't have the data. Or at least we didn't look at it in detail. We could have collected that.
Got it. Makes sense. I'd be very curious. Thank you.
Okay, thank you. Thanks, Crystal. Actually, I have a side note about the measurement. Okay, while the last speaker is setting up, I think before Crystal shared an interesting image of the global south and north, the difference. And we have an experience. My son went to a school trip for Myanmar. We are applying for the visa before the military thing. Then we realized sometimes the website is down. Then we measure a few days. We realized they turn on their web server at 8 a.m. when the office hour starts, and shut down the web server at 6 p.m. when they go off work. Right? I think before the security, there is a functionality measurement to measure whether the web server is properly maintained and operated. Maybe that's another interesting topic. Thank you. Ready?
Great.
Yeah, okay, we have the last paper. Michelle will talk about the security signals, and also there's the two other authors standby. Okay, thank you.
Hello, everyone. I'll be talking about security signals, but let's start with the broad picture. So how we approach web security at Google. Web security is hard, and it's hard to scale, especially at Google. So we have possibly the largest deployment of web applications in the world, 8,000 web services across 1,000 of registrable domains with a lot of traffic. And we also have, like other large organizations, a very heterogeneous ecosystems in terms of programming languages, web frameworks, and so on. Of course, the inclusion of thousands of third-party libraries. And this changes all the time, right? So it's really hard to scale an approach that is based on fixing vulnerabilities one by one, or that is based on security reviews, mostly because the software engineers grow faster than the security engineers. So we realized early that the only way to have a secure ecosystem was to use a secure by design approach. And with that, I mean, there are some publications by Google about that, but I mean, in broad strokes, secure tool, libraries, and frameworks, something that we call the well-lit path, and then internally guidelines and recommendations for developers to keep them on the well path, security reviews that are limited to opt-outs from well-lit paths, and regression monitoring and continuous remediation. So security signals fits into this picture by providing visibility into the security stance of web infrastructure. So mostly it's visibility and observability. It can determine if certain applications are secure by design from broad classes of vulnerabilities, and we'll see how in a bit. It can enable security remediations and also help prioritize them based on exposure. And finally, continuous monitoring of security controls, and in some cases also some kind of automation of, for example, bug filing, so that security resources are spared. So let's start talking about collecting signals and how it works. So security signals, main inputs is real-world HTTP traffic, basically. So our traffic logs. We use reverse proxies as observability hook. And this might be somewhat of a novel approach. Reverse proxies are known for mostly load balancing, termination of HTTPS traffic, protection against DOS, but they also allow centralized logging, and they could work as a perfect observability hook for such a system. Of course, Google processes trillions of HTTP requests per day from billions of users daily, so we cannot log everything. We have sampling in place, so web traffic is sampled, usually 1%. For internal traffic, we sample 10%. We also do not store sensitive data because of policies. We also keep them at very, very short times, just a few days. Of course, access to raw logs is audited, and it's restricted to a very, very small number of justified cases. So what we see in our reverse proxy traffic logs is metadata mostly about the request response pairs. We have cookie metadata, we have HTTP method, destination host, we have paths, we do not see the query parameters, for example, and so on. We never store the request response bodies for both technical and privacy reasons. And we have, of course, the HTTP headers, which sometimes we redact for privacy reasons. And some of these contain security relevant information. So this is something that Security Signals collects. Here are some examples. You might be familiar with some. Security Signals also uses synthetic headers, a synthetic internal header, which we call the ex-Google Security Signals response header, which web applications could return, signaling some extra bits of information that the server knows. For example, how the response has been generated, by which templating systems, and so on. So it's important to note that these internal headers are not sent out publicly, but they are stripped at the reverse proxy levels. But they are still possible to be seen at the reverse proxy level from traffic logs. And this is what Security Signals hooks into. So here are some examples of synthetic security signals. We know the serving web tech stack, which by itself is very valuable information, and it's sometimes not easy to have an inventory of them. So by itself, it was one of the first ones and very, very useful. A pointer to the method or function in code that generated the web response. This is also something that is not obvious. Information about server-side templating systems, applications build environment. Is this like a fresh build? Is it an old build? And then some vulnerability-specific mitigations information. For example, if a cross-site request forgery token check was performed, at how and how. There would be an example, and David will go through that. Another example is server-side isolation policies and fetch metadata. Because some of these logic is server-side, we know when server-side isolation policies are enforced at a server level. Security Signals also uses auxiliary data, what we call auxiliary data, that is like, it means a lot of extra information about a request response pair that is not in the HTTP request response pair itself, so not in headers. For example, information about the production environment, on which machine it is run, ownership information, which team internally owns it, and how sensitive the hosting domain is. We use something, and we blogged about it, called domain tiers. So we tier our origins based on how bad it would be if they get compromised. So this is very important to prioritize remediation efforts. And then source code information and so on. So these are basically other data silos that are internal, but they get, let's say, joined by this, what is called the security signals pipeline, which runs daily at night. It reads yesterday web traffic logs and joins it with security, with auxiliary data. What it also does, and it's kind of important, it reduces the number of entries, because we are talking about trillions of entries, and of course we don't want to store all of them. So an important part is cardinality reduction. What we do is we leverage some of the auxiliary data we talked about, which is path routing information that from many sources of truths to basically have what we call path patterns. So we don't want to have all the HTTP URLs. We want to have path patterns that share code, for example, that are generated by the same code. On paths that we could not have, for what we could not have authoritative information, we use a manually curated set of well-known high entropy paths to redact to avoid cardinality explosion. And on the remaining paths, we execute a machine learning model, which is a very simple one. It's a random forest to basically detect high entropy parts in a path and redact them. And we store this into queryable tables that a subset of engineers could access. They are aggregated, they contain only the identified data, and they are retained for 30 days. This table is used by systems to do automated monitoring and also automated bug filing, since they contain ownership information. And now to David for the use cases.
Yep, so then kind of digging into what exactly we do with all of this data once we have it collected. One great example of this is how we approach mitigating cross-site request forgery bugs, which is this classic web bug where you can have a malicious website trigger a cross-site request and trigger state-changing actions. In this case, example of exploiting a bank. And the classic mitigation for this is you have a CSRF token. It's a token that's attached to the request that is somehow unique and is something that your third-party website wouldn't be able to access. But of course, the next question is, how do you ensure that this is actually rolled out across all of Google, across every single endpoint? So we have this remediation process we go through of creating a synthetic signal where we modify the framework to emit information about whether or not a CSRF check was done. And then we go through the database and we look for endpoints that are state changing, for example, accepting a post request, and see, oh, do they have this synthetic signal? Are they enforcing a CSRF check? And then either that is a vulnerability, in which case we can fix it, or it's a missing synthetic signal, we go and add that, and we can repeat. And this makes it possible to essentially go through every single endpoint across Google in a scalable way to make sure they all enable these mitigations. Another similar example of one of these remediations is around CORS requests, where we found there were a lot of patterns where people were checking the CORS origin in an insecure way. These are kind of two classic examples of this. And we followed the exact same remediation strategy. We identified our CORS-enabled endpoints, looked at the origins of the requests they were receiving, because that is automatically in the tables, and then automatically test them and identify vulnerabilities and fix them. And again, we were able to do this in a scalable way, leveraging the information that's in the database. Another really critical thing we do with this is work on adoption of web security features. So a great example of this is trusted types, which is a really useful mitigation against cross-site scripting vulnerabilities. And the core thing we need to do is add this response header everywhere. And we can use security signals to enable this, where the idea is we can look at what services have this response header. We can identify batches of services that are built on similar serving stacks, make them all compatible, roll it out across all of them. And then along the way, we can create these really great graphs where we can break down what is our traffic coverage, how many services are we covering, what frameworks are we covering, and measure our progress in rolling out these security features. And the last use case that I think is really cool is around measuring runtime dependencies and these trust relationships, which is kind of related to one of the earlier points that someone had made about JavaScript dependencies, where the web is full of these trust relationships. It might be loading JavaScript from a site, it might be CORS, it might be post message, iframes, anything like that. But with security signals, we suddenly have all of this metadata across every single Google service in one location. So we can identify, oh, this is a security critical service that has a dependency on another service. That one is now security critical. We need to make sure we uphold the same high security standards for that service too. And we essentially can do the same thing for any questions we have about Google Web Services. So a current example that is kind of the hot topic nowadays is AI. And what we can do is join security signals with an internal database of auxiliary data about RPC calls. And we can see, oh, this HTTP endpoint triggers an RPC to this AI model, and then we easily get a map of every single web application that uses AI models and how they use them, and we don't have to go product by product to try to understand that. And the last thing we do here is this also enables automatic monitoring and regression testing, where we can define security invariants, such as enabling CSP or trusted types or co-op or any of these important security features. And we can continuously monitor for which services don't have these security features. Does a service ever accidentally turn it off or create a new endpoint without it? And then we can alert either our team directly or using the auxiliary data in the databases. We can even go as far as automatically filing a bug, reaching out to the team and saying, oh, you had a drop in CSP coverage today. Please take a look at this. Let's fix this before it actually becomes a larger issue. And this is kind of the core thing that we really try to do with security signals, is scale our web security approach across thousands of web applications. So then we also have built a whole bunch of front ends, which Lucas will talk about.
Thank you. I'm Lucas. I manage Google's web security team, and as Miki already mentioned, we're a small team. There's thousands of web applications, thousands of developers, so everything we do really needs to scale. And the same applies to our security signals. The mitigations and remediations that David mentioned were mostly driven by our small team. So the question is, how can we make this data set actually accessible to the entire company and to the different user groups that we have there? And basically what we had to do is like three things. On the one hand, we need to aggregate the further up we go. So our security engineers, they can access maybe the raw table directly, but our executives probably less so. And the other thing is adding opinion. Again, the further up we go, the less web security knowledge there is, and that's intentional. So we need to actually interpret the data for them. And last but not least, some sort of UI, UX is usually needed, or a dashboard, to make sure that this data is actually useful for teams, slides, whatever. So let's start with the one UI that we actually have built for security engineers. Somebody does a review or an audit of a web application. They can actually use this UI that is based on security signals and have like a live view of the application, all its endpoints or paths, and for each individual bubble here, which represents such an action or path, they can actually see if all the recommended security features are turned on, and can even like get some more metadata about like, you know, what was this a GET request, what was the status, and what is really useful for our use case, they can directly jump from a URL to the code. So we get like, you know, a lot of vulnerability reports every year. They give us a URL. We have thousands of applications across different frameworks. How do we get from the URL to the application? So that mapping is actually possible through that mechanism, which is really useful in practice. Then we can actually go one layer up. We can actually provide something more aggregated for product teams, where we actually condense our recommendations and safe defaults and guidelines into a UI and back this with live data for their product, their web application, so they can actually go there and see like, you know, does my web application enable trusted types or strict CSP? And if not, they can even like, you know, drill in a bit, get some more information, file a bug, and so on. So it's a very nice self-service way to scale across hundreds of product teams and give them information about their own application that they may not have, and usually maybe request a security review or something. So it's really nice and scalable. And then last but not least, because we have actually this central funnel, the reverse proxy where all the web traffic goes through, we have a complete inventory of all web applications. And since we link that to criticality and information about security controls being present or not, we can actually compute something like an ecosystem health for the entire company and basically say what fraction of our applications use like the recommended frameworks where security is built in and, you know, developers have to file a security review to opt out, or compute a security risk score where we actually measure the residual exposure of a given web application or the company as a whole, and take into account all the individual security controls and their presence on live traffic data. That's also really useful for us as a security team to show the progress we're making, make sure that leadership understands what the highest priority investments are in this space. And yeah, that's about it. And with that, I say thank you for listening. I hope it was useful, and we are ready for questions.
Yes, thank you, the speaker. Any questions?
Hello, Alex Capravelos from NC State. Very interesting talk. Thank you for enlightening us. I have a question about, I didn't understand quite well the refactoring with the CSRF token that you talked about. Like, you have to basically go refactor everything to send the signal if the CSRF token is being used. If you go down that path, why not refactor the code to put the CSRF token always there?
Yeah, so the kind of key bit from a scalability point of view is we do this in various libraries that we maintain. So it's not editing every single application, it's editing the 5 or 10 different CSRF libraries that applications use so that they emit this.
Got it. Okay,
Yeah.
so it's at a different level where you cannot go and apply basically also like directly the CSRF.
Exactly.
That's cool. And also like is there anything of this going to be open sourced or publicly available or like something like that that the academic community can use in the future?
Sadly, it's difficult to open source it because it's built on top of Google infrastructure.
Yeah.
One of the things we do try to do is be public about the data we can. So for example, Mickey had mentioned domain tiers, where we essentially published a list of every single Google origin, hundreds or thousands of them. And we put it on GitHub and tell people, these are the security critical ones. Start with this list if you want to find vulnerabilities and report it to us. And I think we like sharing that data, but it's a matter of finding the data we can share.
I understand. So, yeah, cool work. Thank you.
Good morning. My name is Vinny. I'm a PhD student in Georgia Tech. Thank you for the presentation. I think you guys are doing a really impressive work. My question is related to somehow the data you are collecting. So you said that you get information about the origin of the request to the domain names. So my question is, do you see users coming more from typing domain names or through Google searches or something? Do you have any perspective on that?
Sorry, I'm not sure I got could you say the last part again?
My question is, are users accessing your website through search, or by typing the domain name or something else?
Oh, okay. So this is, for example, one of the questions you could very easily answer with security signals. It's interesting that there are many non-security use cases like this, right? Is it mostly type-in traffic, or is it search funnel traffic? Or another one that, for example, we addressed lately is if they use country code TLDs. And where are they deployed, right? So it's very easy to see this because, for example, we have referrer information, and we have, even though it's redacted, so we just see the host. But so yeah, I would say security signal is something that enables answering those questions. I don't have the answer right now of how much traffic is search funneled. I assume that there are, let's say, second-level subdomains of Google that are still pretty popular, like mail, for example, google.com. But surely search is a big part of it. Yeah.
Okay. I'll be happy to discuss about that.
Absolutely.
Thank you.
Hey, it's Chris from Mozilla. Thanks for sharing all those insights. Obviously, it's very important to roll something out and then collecting the data to instantly can roll something back in case something goes wrong. And I think it was on slide 29. That was one tip I was very curious about. Yeah, it was the blue tip shortly before 2022. Was that rollout of trusted types? And do you remember what happened?
Yeah, we certainly had rollbacks, and sometimes they're we usually, when we roll out a security feature like trusted types, we are using report-only mode to start with, and then we also usually start enforcing with internal traffic, and then very gradually roll it out externally. I don't remember why this explicit case, this drop happened, but there's probably two reasons. either we missed something and we maybe broke like some corner case feature that was not visible, but what also could happen is that for some reason the product just turned it off again, because back in the days we didn't have these rollback protections that David mentioned. Nowadays the framework requires a security review if you turn off a security review, a security feature. And I think back in that time we didn't have that. And for example, I do remember like the CSP of Gmail suddenly disappeared from one day to the other. We luckily had the logging to find out, but I think maybe not at that time of the, in what was it, 2021. So that's one reason I could imagine. But I would be curious, we could look it up.
Very important work, thanks for sharing.
Thank you.
Hi, Marco from Turin. So I've got one request and one question. So about the request, maybe you talked about anomalies. So I guess that you have a collection of a set of rules and you can check like these security signals and the request against these rules. Maybe you could open source like some of these rules. This could be, you know, like a collection of things that might be useful to other companies and also for the academic community. And the question is, can you also record with security signals some discrepancies about requests that should not happen? And then like use these discrepancies to detect vulnerabilities at the web platform level. So not at the application level, but things more on the, you know, web standards and the composition of web standards.
Yep, so I'll answer both of those. So first, for the question, I'll say we definitely have done that in the past. There's one case I can remember where there was a bug in fetch metadata headers that had been raised, and there was a question of, oh, how widely triggered is this bug? And because of security signals, we were super easily able to just go run a query and give an answer to the browser team of, it is this widely deployed, here is the breakage that we expect when we fix this bug. Does that make sense?
Makes a lot of sense, yes.
Yeah. And, sorry, what was the request again? I'm not forgetting.
To open source the...
Yeah. So for the security invariants, we actually just published a blog post about this where we essentially list out all of the security features that we see as critical, and I'd be happy to share the link with anyone who's curious for it.
That's awesome. Also, like, awesome that you call it like security invariants. That's also like what like I'm actually using in my own research, like to call like these properties that should always hold. So thanks a lot.